Good morning, everyone. Welcome to the MIPI CSI-2 Security Framework presentation. Today we'll discuss how the CSI-2 Security Framework for ADAS, ADS provides data protection of camera connectivity to ECUs with component authentication, integrity, and with optional confidentiality, and also explore key features. We are quite fortunate to have presenters Philip Hawks, co-chair of the MIPI Security Working Group and principal engineer at Qualcomm, and Rick Wiedfeld, co-chair of MIPI Security Working Group and senior director at Qualcomm. So, Philip and Rick.
Thank you. Thank you for the welcome. And welcome, everyone. I'll jump straight into it. Okay, what are we talking about today? So today we're going to be talking about the security specification that MIPI has been working on and developing for the protection of CSI-2. This spec is called the Camera Services Extension Spec, and it includes both security and functional safety, but I'll just be focusing on the security part of it. As Harun mentioned, this is the applications that we're focusing on are advanced driver assistance systems and also automated driving applications. And what this has ended up producing is two protocols, one called the Service Extensions Protocol, or SEP, and another one called the Frame-Based Service Extensions Data, or FSED. And these actually share a lot of similarities. The main difference between them is in how the formatting happens, and the SEP allows a bit more fine-grained details. It's more message-based, whereas frame-based is frame-based. These both offer a lot of flexibility, which enable various trade-offs that can be taken advantage of by the vendors, by the integrators, and also it doesn't just mean you've got something that's fixed when you start. In your implementation, there's the ability for the ECU to control what's happening and to change which options are being selected according to real-time system needs. And this flexibility gives the various trade-offs of security level versus the amount of computation that you can afford, and that can be related to the power consumption needs, thermal considerations, etc. We're targeting for having these specs ready in at the end of this year or early next year. At least that's where we're finishing getting the work done. So what were our motivations and what are the goals in what we're trying to achieve here? So on the right, we've got a little diagram there showing the MIPI Automotive system, and we have sensors talking to SoCs and SoCs talking to displays. We're focusing on the talk of the sensor talking to the SoC, and we have considerable volume of data being transmitted by the sensor to the SoC. We have tens of gigabytes of data for multiple cameras, multiple sensors distributed around the car. And we've got to get that image data from one end of the car to the other. We've got distances of like 10 to 15 meters of cables. So this is a bit different to what MIPI started off with, the type of distribution that MIPI originally focused on. Pardon me. Now the primary goal, this isn't the only goal, but the primary goal for us is making sure that sensor data gets to the SoC unaltered. That means that the ADAS and ADA assisted driving programming can use trustworthy data, and also make sure that your displays are getting the feed of the correct data from the sensors. There's other considerations which I've got there, but I'll skip those for the moment because that's really the main thing. I guess the one that I'll also mention is that we've got optional confidentiality. That's to protect location revealing images or images that might have some privacy implications. And we use message encryption to protect against that. For the making sure the sensor data is unaltered, what we use there is called a message authentication code, or MAC. And we think it's helpful to see where the security is being applied in the stack. This diagram here is a variation on the layering diagram in the CSI-2 protocol specification. And this diagram is from this Camera Services Extensions, CSE, specification that I mentioned earlier in the talk. Our CSE provides CSI-2 traffic with a variety of services, including functional safety and security. And where this is located is just above the lower level protocol. Now, we're not expecting, you don't need to understand the lower layer protocol to understand this talk. The important thing is that it's up near the application layer. So it can be data type aware, which means that we can make decisions on what security is being applied based on the type of data that's coming through. And that means that we can really focus our efforts on the data that needs protecting. What our efforts have produced are 3 separate protocols. We're only going to be focusing on the first 2. The SEP and FSED are there to protect the CSI-2 data, the image data, and they provide end-to-end security. So does the CCISE protocol, but the CCISE protocol is not protecting the image, the data plane messages, it's protecting the control messages. Those messages sent over I2C or I3C for controlling the camera. So I won't go into more details about CCISE. I'll focus on SEP and FSED. So the difference between this is that SEP has a granularity, or it's message based. So it looks at each packet and it processes on a packet by packet basis and can focus down to that level of detail, whereas FSED is more frame based. And I'll provide more details in a couple of slides. But before I do that, it's good to have a bit of background here about what a frame what the data looks like, the image data looks like. Graphic here is showing what the existing CSI-2 frame looks like. So we have our sensors distributed around a car, and each sensor can transmit data in multiple virtual channels. So multiple sensors can have any number of virtual channels, and these can end up being aggregated by aggregators into and interleaved. And so a single PHY can support multiple virtual channels, and each virtual channel is a sequence of frames. So in particular, if you think of like video data is a series of snapshots of frames, and each frame is like one capture from the sensor. Each frame is a sequence of MIPI CSI-2 packets. It starts with a frame start packet up here at the top and on the right, and then has a frame end packet to finish the frame. And in between, there are three blocks, three different types of data that are transmitted. There's some initial embedded data, then there's some image data, and after that, there can be some more embedded data after the image data as well. So this divides the frame up into 5 what we've called frame partitions, FP1 through to FP5. Just keep that image in mind, because in the next slide we're going to show you what happens after FSED has been applied to this CSI-2 data. We've shown FSED on the left here and SEP on the right. So you'll recognize the frame partition from the previous slide, FP1, FP2, FP3, FP4 through to FP5. In the case of FSED, those frame partitions haven't been altered, with one minor caveat, and that is that you can encrypt the payload if you want. But otherwise, the contents of those frames haven't been altered. There's no new headers in those frames, in those packets. Sorry, the packets haven't been altered by new headers or new footers or anything, but we've introduced new messages which get inserted into the frame. As there's always in FSED, there's always a control sync sent at the start of the frame, which ensures that the receiver of the frame knows the sender and receiver are synced on what security is going to be applied to that frame. And then there's a frame tag at the end. Now, all of these include a MAC, which means you can check that checks the integrity of the messages. The control sync MAC just verifies the control sync. The frame tag at the end, the MAC there, it either covers that. We've got two options. One is that we can split the entire frame in two parts. The top block, we can have a MAC which just verifies the top block, so you can verify the top block before you do further processing. And then you'd send a second the frame tag at the end, which would cover the middle block and the bottom block, FP3 and FP4. So that's one option. The other option then is that you've just got one. You don't have that top tag. You just have the frame tag at the end, and it includes a MAC which covers all the message. On the SEP side, you can see there's no new messages introduced. So you've only got the original the packets, the same number of packets as you had before, but those packets have new SEP headers inserted at the start of the payload, and optionally SEP footers at the end. And these SEP footers, from the security perspective, the footers that can get added are these MACs, these message authentication codes. And there's various options for when you can transmit those message authentication codes, and I'll talk through those when we get to that in a couple of slides' time. So that's the difference between FSED and SEP. But the actual processing of the data that comes in is otherwise almost identical. And all the options are available for both FSED and SEP. So we'll start going into looking at what those options are. So the options that give the vendors flexibility, give the integrators flexibility in how they're going to implement things. So the first area we're going to look at is in terms of crypto algorithms. And we've designed these for two general classes of sensors. And a sensor could fit into, I mean, there's a spectrum of sensors. So exactly where your sensor fits in depends, is your choice. But we've generally got where we've focused on efficiency sensors, providing options for efficiency sensors, which have lower bandwidth, lower gigabytes per second, and they're meant to be less complex, and they can't afford the additional hardware to perform crypto operations. On the other end of the scale, we've got performance sensors with higher GPS, gigabytes per second, but these higher performance ones can afford additional hardware to support this higher gigabits per second. And so we've got algorithms designed to focus on those two cases. And where we're not dictating which one has to be used, it's both of them are optional. So the efficiency algorithms or the E algorithms, they use AES CMAC. Don't need to worry, but no encryption. So all they do is support integrity protection. They can use AES hardware for integrity only.
We're good to continue. So in terms of there are different aspects of flexibility that Phil started to describe. This particular one is about the crypto algorithms. So he did start to identify the efficiency versus performance kind of category of sensors. And each category, whether it's an efficiency or performance, has its own type of integrity protection. Put simply, it's CMAC versus GMAC. Essentially, the lower performance or the efficiency algorithms are also not configurable to support encryption. And then, of course, with GMAC, encryption, of course, is available as an option. Both of these performance modes support 128 and 256-bit keys. And naturally, the ECU is in charge of, identifying, what the sensors are capable of supporting and then configuring them, appropriately with the, with the particular keys. Phil, I see you're back. Are you good to continue? I just finished up this particular slide.
Awesome, thank you. Can everyone hear me?
We can.
You can? Okay, thank you. Okay,
yep.
I'll jump to the next one. Sorry about that, folks. Okay, so that was the first area of flexibility that we provide. The next one is what we call tag modes. So on this slide, we're showing the tags for FUSA and security. Security has a message authentication code, and FUSA provides a CRC, which can be used for checking bitwise error correction, bit errors. And the tag mode identifies when one of these tags is going to be sent within a given frame and which packets are covered by the tag. So we've again got our frame partitions shown here on the left. And we've got the frame data, which is the frame start, some embedded data, some image data, some embedded data, and finally the frame end again. Now, before I go any further, the important thing to say is that there's always, all of these packets, there's a MAC addressing that data. So the tag mode doesn't mean that they're, so it doesn't matter which of these options you're using, that doesn't mean that you're not protecting data. For SEP, because we have granularity, we can send those footers on every message. We have quite a bit of flexibility in when we send a MAC. we've provided three types, three tag modes. The first one is per message, which means we put a MAC on the end of every message, which makes it easier to means you can tell for each message whether there's been some sort of issue in the transmission and whether that then detect any integrity problems, whether the content has been altered. And that comes at the cost of transmitting a MAC on every message. But that is actually fairly small overhead compared to the size of the image data. A MAC is the size of the MAC is almost in the noise. On the second type, second tag mode we've got is per data type. And what that means is that we look at blocks of data types, and like each block has just a single data type, whether it's embedded data or it could be RGB data or any other sort of data. And you only transmit a MAC when you get to the end of that block of data. So we've got one MAC at the end of, there's always a MAC in SEP sent on the frame start. And then because the top block is all the same data type, we'd send a MAC at the end of that. Within the middle block, there could be multiple data types. And so we would send a MAC at the end of each of those data types. So here we've got two, we've shown data type 1 and data type 2, and put a MAC at the end of the data type 1 block, and then another one at the end of the data type 2 block. And then another MAC at the end of the bottom block. And the final tag mode we have for SEP is per frame. And this is similar, this is fairly close to what happens for FSED. There's a MAC on the first message. There's always a MAC on the first message. There's always a MAC on the last message. And we allow a MAC which just covers the top block, optionally in the middle. So you've got, it sort of covers two options. One where you've got a MAC which covers the top block, and then at the end you've got a MAC which covers the middle block and the bottom block and the frame end, or else you've got this MAC at the end which covers everything. FSED just supports the one mode. It always looks the same. I talked to that a couple of slides ago, so I won't go through that. But it's very similar to the per frame mode for the per frame tag mode for SEP. This slide shows the next level of flexibility, which is in choosing what we call security variants. So we've got 5 security variants, and they range from having, well, let's divide them in 3 parts. There's first two have full integrity, so they always protect everything. And there's the option to either have encryption on, which we've shown with yellow, or encryption off, in which case there's no yellow. We only support doing encryption when the data is fully protected. The second set we have is called partial integrity. So what this means is that we haven't protected all of the video data in applied integrity. We haven't applied integrity protection to all the image data, but we've selected we've selected which data we want to protect. And the reason we do this is because there's redundancy in the video data. So if we're not protecting everything, that should be okay, because we protect it enough so that an attacker can't influence decisions by altering those lines which aren't protected. So we can either have horizontal stripes. So the blue shows you what's integrity protected. So SV3 protects entire lines and then can skip some lines. SV4 operates more in terms of protecting particular byte pixel positions within a frame. And lastly, we have the the option to turn off the security, which, well, I'll switch to the next option. This isn't saying that we're not going to protect anything in the frame. It just means that in terms of the payload, we're not going to protect the payload for a particular block. So let's skip to the next slide. So in the figure to the right, you can see the different security variants that are available, and you can see that different security variants are available for different frame partitions. The frame start and frame ends, FP1 and FP5, they only support full integrity with encryption off. And then the top block and bottom block, they support more options. They support adding encryption with full integrity with encryption, full integrity without encryption, and also these options where they have line-based partial integrity, where they just protect the first line of the embedded data. So this assumes that you'll put all the important data in that first line. And the middle block, where you've got all the image data, that supports more options. It's got these stride patterns, we call them, which gives you this striping, either the horizontal striping or the vertical striping. And lastly, for each of the top block, middle block, and bottom block, we've got the option for no integrity and encryption off. And the idea is that depending on what you can support in your sensor, you can or the integrator can choose what's going to be protected and how it's going to be protected. So you can make different selections for the top block, middle block, and bottom block. So we show an example here where we've got the top block encrypted and integrity protected. But then for the middle block, we've got these vertical stripes that we're protecting in the frame. And then for the bottom block, we're just protecting the first line of that bottom block. The main point of this slide is that vendors can get to choose which of these options. We've looked at these options for the last few slides. Vendors can choose what options they want to implement. Integrators can choose which of the supported options they then use in their system. And they can also use the ECU to control those security operations based on system needs in almost real time. It can change everything on per frame if you want. And lastly, this is just repeating what we said at the start. So I won't cover this. Just to say the specs that we're working on for this, the CSE spec, the CCISE is going to be defined in a separate spec from CSE. Those two things we're targeting for December 2002, as well as the MIPI security spec, which it covers how you manage the security sessions for CSE and CCISE. Apologies for the interruption in my data connection earlier on. Thank you for the opportunity to talk. I'll open it up for Q&A now.
Yeah, thank you, Phil and Rick. Excellent presentation on the security framework. Our first question is, can you speak to and perhaps elaborate on stride pattern and partial integrity? I believe there was a reference to stride pattern on slide number 11. Thank you.
Okay, so these stride patterns are applying in these two columns here, where we have the line-based stride pattern and a byte-based stride pattern. So in these cases, what the stride pattern does is describe a pattern for which, in this line-based one, which lines are going to be selected and input to the Mac engine, and which ones are going to be skipped and are not going to be input. So in this simple example here, we've started at the first message in the middle block. We've kept that and put that into the Mac engine. we've skipped the next one, and then we go through a cycle. Basically, it defines a cyclic pattern of keeping a number of messages, then skipping a number of messages. So it depends on what parameters you want to do. And the same approach is used for the byte-based stride pattern. It's just that in that case, you're counting bytes in every message rather than counting cross messages. Good question.
Yeah, that actually makes a lot of sense, Phil. We have a second question. Zooming out, based on the read of the present ecosystem, why is camera security becoming so important recently, and perhaps like why did MIPI begin this activity?
Well, the real motivation was the advanced driver assistance systems and automated driving becoming more and more of a priority. We really need to ensure that that data is not getting altered, modified. So we need some sort of protection on that, and that's the integrity protection that we get with a Mac. And so that was the main driver was that, and we did so seeing this coming up, the security working group, and it was in a different form. It was an investigative group originally. The members of that group did an analysis of that situation to work out what the priorities were and what sort of functionality we needed there. And so that included confidentiality or hiding the data.
Great, thanks, Phil. We have one additional question. As co-chairs of the work group leading the composition and writing of the CSI-2 security specification, can you speak to perhaps some of the hardest, difficult things you came across, and perhaps what were the challenges?
Sure. There. Yeah. So what was some of the challenges? So one of the things which we haven't gone into much in this presentation, but I think we went into last year's presentation, was how do we do the authentication? How do we set up these secure sessions that we're going to have? And there was work in a group called DMTF, and they've been working on a specification called SPDM, which was fitting this bill. So it was work in progress at the time, and so we've sort of been keeping in touch with them and reviewing their output, and we decided that the SPDM specification would fit the bill for what we were doing. It's sort of based on TLS, which is it's got a big group of experts there, and it's basing what it's doing on TLS, which is used across the internet, and protecting this I'm sure it's probably protecting this stream that we're present in at the moment. The other things that were challenging was the variety of sensors. So the fact that we do have these sensors for which we can't afford to put mountains of crypto hardware into, because it just won't be feasible. And on the other hand, we're going to have some sensors which can afford to do that, and which are going to need that amount of security, and supporting everything in between as well. So designing a system which would support that, and which got these stride patterns, that seems that's a fairly unique solution that really targets what CSI-2 is protecting. that's taken a lot of work getting that coming to a common answer to that problem.
Thank you, Phil. I would like to again take this moment to thank Phil and Rick for providing an incredibly detailed and valuable presentation on MIPI CSI-2 security framework. Thanks again, Phil and Rick.
Thanks, Arun. Thanks, everyone.
Cheers.